Welcome to Tools for Studying Patterns of Change. Our objectives in this lesson are to find relationships between variables and represent them as algebraic rules. In your work on previous lessons, you studied a variety of relationships between dependent and independent variables. In many cases, those relationships can be expressed by rules that use letter names for variables. For example, the stretch length L, we called it, of a simulated bungee cord depends on the attached weight W in a way that is expressed by this rule. L equals 30 plus 0.5 W, where L, remember, is the stretch length of the bungee cord, and W then was the weight. So we're relating these two variables. Let's look at the second example. The number of customers N for a bungee jump depends on the price per jump, P, in a way that is expressed by this rule. So we know that N is the number of customers and P is the price per jump. And the final one we looked at before was the time T of a 500-mile NASCAR race depends on the average speed S of the winning car, and it can be expressed by this rule, which, if you remember, we derived from the distance equals rate times time formula. These symbolic rules give directions for calculating values of dependent variables from given values of related independent variables. They also enable the use of a calculator or computer tools for solving problems. If we have a formula that we can put in our calculator or in our computer, we can solve multiple problems over multiple time periods based on this rule. Communicating with symbols. The first challenge in using algebraic expressions and rules to study a relationship between variables is to write the relationship in symbolic form. There are several ways information about relationships occur and several strategies for translating information into symbolic form. So as we work on the problems together in this lesson, look for answers to this question. What are some effective strategies for finding symbolic expressions that represent relationships between variables? Listed below are some symbols you already maybe recognize and use. When you see a symbol like this, it brings to mind the fact that maybe campfires are allowed or there's campfires in this area. Other symbols that you use commonly are, for example, the dollar sign or maybe the percent sign. You know exactly what that means. That's what we're going to be doing today, using symbols to represent a variable. Translating words to symbols. In many problems, important information about a relationship between variables comes in the form of written words. Sometimes it is easy to translate those words directly into algebraic expressions. Let's look at this example. If a restaurant adds a 15% gratuity, in other words, a tip, to every food bill, the total bill T is related to the food charges F by the rule. What is the rule? Pause the video and see if you can write a rule. Maybe you wrote this rule. T equals F plus 0.15 F. What does all this mean? Well, we know that total bill is represented by T, so T is our total bill, which includes our tip plus our food. F right here represents the food charges. So this is what we paid for food. So maybe we got a hamburger, maybe we got some French fries. That's the cost of that. 0.15 is our gratuity or our tip. We know that a tip, 15%, is charged on our food. So when we multiply 15% by whatever the cost of our food is, this total amount right here will then represent our tip. Notice we're taking the food plus the tip to give us our total food bill. Let's look at another example of how we can translate words into symbols. So in other cases, you might need to calculate the value of the dependent variable for several specific values of the independent variable. In other words, make a few calculations on your own using the skills you have to see how the two are related. So let's try an example of what that looks like. Suppose that a library loans books free for a week, but then charges a fine of 50 cents each day the book is kept beyond the first week. To find a rule relating library fines for books to the number of days the book is kept, you might begin by calculating some specific fines. So how would you do that? Pause the video, think about how you might do that, and then come back. You might have made some calculations like this. The fine is going to be equal to 50 cents for every day over 7. So you may have said, well, let's just pretend that I've kept the book for 10 days. I would have had it for 3 days in which I paid 50 cents per day. Maybe I kept the book for 21 days. How would I calculate my fine? Well, you might have paid 50 cents for every day over 7 days. In other words, 21 minus 7. So how can we take this then, this information, and create a rule that will work for any number of days in here? Again, pause the video and see if you can use symbols to create a rule. Okay, well, we know that we need to use F for the fine and D for the number of days. Well, our fine we wrote in words, so we can just replace that with F. Our fine is going to be equal to, we know this has to stay the same. We have to take 50 cents and multiply it by the number of days over 7 because the first week is free. Well, we could replace the number in here with D. And we would still subtract 7 because the first 7 days are free. Now, this could be used for every member who checks out a book, except for, what if a member only checks out a book for 6 days? Well, that would be a strange calculation. So we might want to just put a restriction on this and just say that the days have to be greater than 7 in order to use this equation. How about this example? Midwest Amusement Park charges $25 for each daily admission. The park has daily operating expenses of $35,000. In this example, we're going to first calculate some things and then try to make a rule. So what is the operating profit or loss of the park on a day when 1,000 admission tickets are sold? Well, how would you do that? Well, we would look here and say, well, we get $25 for each daily admission, so I know that I would need to take $1,000 or 1,000 people, that's how many people or tickets that I sold, and I would need to multiply that by what we charge for each person, and that's $25. But we have operating expenses each day of $35,000. So whatever we make, this is our income, let's say, we're going to have to subtract what it costs us to run the park. So we would need to subtract all of our expenses. That is how we get profit. And our expenses are $35,000. Now this isn't an equation yet. In order to be an equation, we need to have it equal something. So what should this equal? Well, notice what we're finding. What is the operating profit or loss? So what this equals would be our operating profit or loss. Let's go ahead and perform the calculation. When we solve this equation, we have 1,000 times 25, which we know to be 25,000. And 25,000 minus 35,000 gives us a loss, we're in the red, of $10,000. What about B? On a day when 2,000 admission tickets are sold. So instead of 1,000 here, we're going to put 2,000. 2,000 times 25, well, that would just be double the 25,000, so that would give us 50,000. Our operating costs, our expenses, in other words, stay the same. So if we sell 2,000 admission tickets, then we actually are in the green now. We have positive $15,000 that we're making. How can we then write a symbolic rule showing how daily profit P, so notice we're going to use this symbol P to represent our daily profit, for the park depends on the number of paying visitors N. So we're going to use N to represent the number of paying visitors. How can we take what we did here in our heads and turn it into a symbolic relationship? Pause the video, come back and see if you can do this. Well, hopefully this is what you got. Our profit, P, daily profit, is equal to 25, which is what we did here, times the number of admission tickets or paying visitors, minus the 35,000. It's not too bad. Let's do one final example. Let's look at a geometric formula. Many of the most useful symbolic rules are those that give directions for calculating measurements of geometric figures. You probably know several such formulas from prior mathematics studies. Let's look here at this rectangle. Figure BCDE below is a rectangle. Assume that you used a ruler to make measurements, from which you can estimate the perimeter and area of this rectangle. A. For any given rectangle, what is the minimum number of ruler measurements you would need in order to find both its perimeter and its area? Well, to be efficient, you would really only need 2. So what sets of measurements will meet that condition? What are the 2 measurements? Well, we know that we would need to measure this distance here, which we could call our length, and we would know that we need to measure this distance here, which we would call our width. Why is it we only have to measure one length and one width? Because you know that a rectangle has 2 sides that have the same length and 2 sides that have the same width. What about B? What formulas show how to calculate perimeter P and area A of a rectangle from the measurements described in Part A? Well, if we think about it, we can do it a couple of different ways. We could say that the perimeter is equal to the length plus the length plus the width plus the width. Notice I'm using symbols to represent my length and to represent my width. This is a very long formula, so I could write it in another way. I could also say that P is equal to 2 of these lengths, so 2 times length, plus 2 of these widths, 2 times width, or W. This is very simple and I can use it for any rectangle. How about area? Well, when we're working with area, we know that area is really just our length here times our width. So again, using my symbols, I can write L times W. There's other ways to do area as well. If we knew how many units were in here, we could add up all the units to find the area. But this is probably the simplest. And this concludes our lesson today on communicating with symbols and tools for studying patterns of change. So hopefully at the end of this now, you know some effective strategies for finding symbolic expressions that represent relationships between variables.